Today we're going to discuss the concept of hybrid orbitals and covalent bonding in chemistry. The concept of hybrid orbitals is a very important one, and it describes the mixing or the combination of individual atomic orbitals on the same atom to form new orbitals on that atom that are more suitable for forming covalent bonds, thereby assembling molecules. Recall that when we talked about hydrogen, we were discussing simply s orbitals. Now, if the hydrogen atom is going to be making covalent bonds, it has only one electron in a spherically symmetrical s orbital to share. So, for example, in molecular hydrogen, two atoms of hydrogen, each with one electron, combined, and you formed a covalent bond, which had electron density along that internuclear axis. Bonds of this nature are really quite strong, but hydrogen is unique in that it can form a covalent bond with that single electron that occupies its half-filled s orbital. The bonding patterns of other elements are not so simple, and for that reason, we need more elaborate models to explain how other elements form covalent bonds and hence molecules. Let's consider carbon, for example. So we've seen methane, which is CH4. Okay, here's its Lewis structure. There's its three-dimensional structure. Recall that methane has a tetrahedral electron geometry about that central atom. It also has a tetrahedral molecular geometry, or shape as we referred to it. Now let's focus on that central carbon atom for a moment, and let's think about the atomic orbitals that are present in carbon. So for carbon, we have the 1s and the 2s, and then three degenerate 2p orbitals. And when we filled those with electrons, this was the ground state electron configuration. Now, where we really want to focus is on the valence shell, the second shell of carbon. And remember, even though we write these ground state electron configurations out in a single line, these orbitals or subshells are not all of equal energy. So the second shell is going to be of higher energy than the first shell, and within that second shell, you're also going to have this degenerate subshell of these three 2p orbitals that's going to be higher in energy than the 2s orbitals. And so this is what we really have in the ground state electron configuration. But we would really run into some trouble if we tried to use these atomic orbitals, just as they are, to form covalent bonds leading to molecules. If we look at this carefully, we see that it can only form two bonds because only two of those electrons are unpaired. That would definitely present us with some problems. For example, if we tried to make a molecule between carbon and hydrogen, this would be the result by combining two of the hydrogen atoms, s orbitals, with the two half-filled p orbitals on that central carbon atom. And then we would be left with these two unpaired electrons in the s orbital that was filled in that atom. This would not be a stable molecule, especially because that central carbon atom does not have a full octet. It is not satisfying the octet rule. So if we want to talk about the formation of stable molecules, we need something more here. We need something better. Well, we know that carbon needs to form four bonds. So how about if we were simply to take one of the electrons in that filled 2s orbital and promote it into the empty 2p orbital? And that would give us four unpaired electrons in the valence shell. And that would explain how we could form four bonds. But this still is not the answer. Sure, carbon would be able to form four bonds. There's no doubt about that. but it would be doing it with two different types of orbitals. Moreover, we've already seen that the two p orbitals are at right angles to each other. They're orthogonal. And the s orbital is spherical. We know methane doesn't look like that. It doesn't have its hydrogen atoms at right angles to each other, and it doesn't have one of those hydrogens roaming around a spherically symmetrical orbital. So we need a better model here in which all of these orbitals are going to be able to be equivalent to each other. So what chemists proposed to explain this and get around this dilemma was that carbon does not form bonds with pure s or pure p orbitals. Rather, as it's approaching another atom to form a bond with it, the s orbital and the three 2p orbitals combine or hybridize to form a set of hybridized orbitals. Each member of this set of four new hybridized atomic orbitals is called an sp3 orbital. And this set of four orbitals was derived from an s orbital and three 2p orbitals, hence the name sp3. And notice that this set of four hybridized orbitals consists of degenerate orbitals, all of the same energy, and that energy is intermediate in between that of the p and the s orbitals from which they were derived. Mathematically, we can refer to that process through which we derive hybrid orbitals as a linear combination of atomic orbitals. And though a sp3 hybrid orbital does resemble a p orbital more than it resembles an s orbital, it isn't a p orbital. Notice that it's lopsided. It has a large lobe and a small lobe with a node in the middle. And the large lobes are pointed towards the corners of a tetrahedron. And that's where bond formation is preferred to occur. So that explains the bonding pattern in methane, where you have four hydrogen atoms, each with an unpaired electron in their s orbitals, overlapping with the unpaired electron in each of the four hybridized sp3 orbitals on carbon, thereby creating a molecule that is tetrahedral in shape. Well, so how can we explain the bonding patterns in other molecules that carbon forms, namely those with double bonds and triple bonds? Here you have an example of an alkene named ethylene. So ethylene, we know, has a trigonal planar electronic geometry. That means it only has three regions of electron density around its central atom. In order to accomplish this, it doesn't need to hybridize all four of its atomic orbitals in its valence shell. Rather, it just needs to hybridize three of those four orbitals, namely the 2s and only two of the 2p orbitals. The other 2p orbital is not a hybridized orbital, but rather it is carried along as an unhybridized atomic orbital, and this results in two different components of that carbon-carbon bond. One of them is the sigma bond, that is the bond that's formed from the end-over-end overlap of the hybridized orbitals along that internuclear axis between the two carbons. And the other component of that double bond is called the pi bond, and that results from the side-to-side overlap between those two p orbitals, each containing a single electron. And you see that that overlap occurs both above and below the plane of the molecule. And you can see that a double bond consists of a sigma bond as well as a pi bond between the two carbon atoms. And the pi bond is not forming a new region of electron density. Rather, it is simply piggybacking on that same region of electron density established by the carbon-carbon sigma bond. Now, for alkynes, we can extend this same concept further. Shown here is the simplest alkyne, known as acetylene. Recall that we had established that this molecule was linear in shape. And for that reason, the two regions of electron density around each carbon atom want to be as far apart as possible. The bond angle should be 180 degrees. Well, to establish that kind of electronic geometry, we only need to hybridize a pair of atomic orbitals, namely the s orbital and just one of the two p orbitals. And so in this case, we'll call that a pair of hybridized sp orbitals. So that's going to exclude these two unhybridized p orbitals from the hybridized system. However, those two p orbitals on each atom still take part in bond formation, piggybacking on the region formed by the sigma bond that results from the overlapping hybrid orbitals. And so you can see one of the pi bonds has its electron density extending above and below the plane shown in this illustration, and the other pi bond has its electron density in the plane shown in this illustration, extending out in front and behind the carbon atoms. Now, this is not a planar molecule. Acetylene is a linear molecule. Its electron density is axially symmetric, but the plane here is just being shown for illustration purposes, emphasizing the perpendicular orientation of the two pi bonds with respect to one another.